Hello, my name is Walter Unglaub, and this is the observer effect of quantum physics. So, in quantum physics, we have discrete systems. We have a few particles that we typically consider, or maybe a system with many particles, but certainly not continuous systems in all cases. And the dynamics of the wave function that describes the set of particles or particle in the physical system is described by the Schrodinger equation. So here, this is an expression of the time-independent Schrodinger equation, which if I write this in Dirac notation, I have an observable, here the Hamiltonian, which is an expression of the energy in the system, and when it is applied to a state vector, psi, then I have the energy, which is the eigenvalue for the matrix representation, or eigenvalues for the matrix representation of the Hamiltonian, times the same state vector, psi. So this is a vector, this can be represented by a matrix, and this is a scalar, or a set of scalars. And what's going on when you make an observation, this is known as a measurement. So when you make a measurement, what you're doing is ultimately you're recording the value that you measure of this eigenvalue. We don't necessarily have to apply this Hamiltonian operator. There are many other operators which represent these physical observables, but these observables aren't actually the numbers that we measure. We measure the eigenvalue. So, in quantum mechanics, it is a probabilistic theory, and if I have a different set of possible values that I can measure, there will be some probability distribution associated with these different possible outcomes. When I measure a physical system, when I perform a particular type of measurement, what happens is that this probability distribution ceases to exist. There is just one value that I measure, because in one experiment you cannot measure a distribution, you just measure one number. And this is known as the Wavefunction Collapse if you work back from the probability, which is defined in terms of the wave vector, the wave function. So this represents a probability distribution, and when you make a measurement, you're just looking at one value of the state. And this raises a lot of interesting questions in quantum mechanics regarding the interpretation of the measurement process. Because once you've made this measurement, if you continue to make measurements on this physical system, the system is stuck in this eigenstate of your observable. This is known as the quantum Zeno effect. In many quantum systems, and you can essentially keep a two-level system like an atom from decaying by constantly measuring it. And there are ways to interpret this in classical settings, but the question of what actually occurs during this highly nonlinear process is still open and up for grabs. So the two most common interpretations are that of the Copenhagen interpretation, which essentially states that you can have a superposition of quantum states, and when you make a measurement, you are actually creating that particular state that you measure, or Everett's many worlds theorem, which has been gaining some popularity in the recent past. And this interpretation states that when you make a measurement of a quantum system, the universe branches out to all the different possible measurements of the system. and we find ourselves in the one in which we measured that particular value. So work and continued research is being done on attempting to learn more about what this highly nonlinear process entails for entangled systems and other exotic quantum states of matter. My name is Walter Unglaub, and this is the observer effect of quantum physics.